In this video, we look at equations involving exponents and logarithms. When looking at exponential equations, if we can get both sides to have the same base, then the only way they are equal is if they have the same exponent. So for this problem, we have a base of 3 and then technically a base of 27. What we want is the same base. Now 27 is the same thing as 3 cubed. So we have 3 to the power of 2x plus 1 equals 3 cubed. We have the same base on both sides. The only way these two things are equal is if the exponents are the same. So we can rewrite the equation as 2x plus 1 must equal 3. So we just solve that. Divide by 2. And we get x equal to 1. Once you have the same base, you can actually remove the bases and get just the exponent, and that gives you what you're trying to solve. Okay, this problem, same idea. We want similar bases, whatever that might be. On this side, we have a base of 9. This side's kind of messed up. So let's try and make this right-hand side a little bit nicer to work with. So first off, I can rewrite this to the -1 power. That's the same thing as flipping it, if that makes sense. The cube root of 3 is the same thing as 3 to the 1/3 power. And then a power to a power is the same thing as those multiplied. So we have 3 to the -1/3 power. So now our problem is 9x equals 3 to the -1/3. Well, 9 is the same thing as 3 squared. And now we have a power to a power, 3 squared to the x power. So we can just multiply those powers together. And now we have the same base. So the only way these things are equal is if their exponents are equal. 2x must equal -1/3. Divide by 2. Whenever you're dividing a fraction by some just number, that's the same thing as multiplying the denominators. It's the same thing as just saying multiplying by the reciprocal. The reciprocal of 2 is 1/2, and you're multiplying those things together. So really we just have x equal to -1/6. Okay. For this one, we just want to get x by itself. This one's actually a little bit simpler in its solving, I think, because the first step would be to divide by 4. We have e to the 7x equals 10^273 over 4. And then to get x by itself, we're going to take the natural log, which is the same thing as a log base e, because those cancel. And now we have 7x equals the natural log of 10^273 over 4. And we can divide by 7, giving us x equal to the natural log of 10^273 over 4 divided by 7. Let's put that in a calculator and see what we get. 10^273 over 4 gives me approximately, I'll do approximately 1.12, 16. We'll just round to 4 decimal places. So that's what we're looking at for our answer. Okay, this one is a little weird. 7 and 3 are the different bases, right? However, 7 and 3 are both prime. It's going to be easier to think of this as, let's make one side have the same base. Now, I'm going to make them have the same base of 3. So, to do that, what I'm going to do is put the one side, I'm going to put this side, in the power of 3. But I can't just do that, right? If I were to do that, I'd be changing the problem. So I also have to put in what undoes the 3, namely log base 3, and then put that in the power, 7x plus 1. And this whole thing equals 3 the x plus 2. So to prove to you that it's the same thing, all I have to do is cancel the 3 in the log base 3 because they're inverses of each other, and we'd be left with the exponent. Well, that exponent is the exact same thing as this. So I actually haven't changed the problem at all. I've just put in a function and its inverse. I can do the same thing if I were to say x equals 2. I can do the exact same thing by saying x plus 1 minus 1 equals 2. As long as I put a function in and its inverse so that they cancel, in this case plus 1 and minus 1 cancel, then I have not changed the function, the equation around at all. This is still the exact same thing as this, just written in a different form. I can do the same thing with an x times, 18 divided by 18. It's still the same idea. I'm doing the multiplication and the inverse of multiplication, which is division. In this case, in our problem case here, I'm doing exponentiation and taking a logarithm of it. And those will always undo each other. Therefore, they don't change the problem at all. However, it does allow us to solve this because now we have the same base. We have a base of 3. So those can be removed, and we have log base 3 of 7 to the 2x plus 1 equals x plus 2. Now this might be a little bit weird, like, well, how does this help us? Well, now we have a base with something in power on the inside of a logarithm. And in the previous video, we can use a property of logarithms that moves this power to the front. We have 2x plus 1 times log base 3 of 7 equaling x plus 2. And I can solve this. I'm going to first distribute the logarithm. I'm going to go 2 log 3 is 7 times x plus log 3 of 7 equals x plus 2. I'm going to get the x's to one side by subtracting x. And I'm going to subtract log base 3 of 7 to the other side. I'm going to write that up here. Let's see, I've got 2 log base 3 of 7x minus x equals 2 minus log base 3 of 7. I can undistribute or factor out an x from this, so I get x times 2 log base 3 of 7 minus 1. 2 minus log base 3 of 7. And now I can divide by this thing here in parentheses. Just going to divide by that again. X equals 2 minus log base 3 of 7 over 2 log base 3 of 7 minus 1. And this we can plug in a calculator to see what the approximation is. I'm getting approximately equal to 0.09. It doesn't continue on. I rounded it to two decimal places because it's 0.08997, and that would just run up to 0.09. So that's what it's approximately equal to. Really briefly, I want to talk about which strategy you should use for these problems that I've gone over. Here I have this first problem, and I chose to do this common base thing that I had here. And the way I did that is because I knew that 3 and 27 could be made into the same base, namely base 3. That's why I chose to do this method. You could just do the natural log, log base 3 on both sides. That would work just fine. But I think it's easier to do it this way. It's an easier idea to work with when you know 27 can be written as base 3 cubed. The same thing is true for this problem here. I chose to rewrite this in the same base. I knew 9x could be written as 3 squared, and I knew this one can be changed to a power of 3. That's what I have right here. And you may not know it at first what to do. Sometimes it's easiest just to try doing some algebra on it and see where it gets you. And then you can figure out, okay, well, let's do this strategy then. So yeah, you could take log base 9 of both sides and rewrite this as base 9, but it's easier, I think, to think of this as base 3. It's always easier pretty much to go to a smaller base, like base 3, rather than a larger base like base 9. For this strategy here, E is not a base, so that's really easy to work with, especially since 10,273 cannot be written as E as base E. That's because base E it's a irrational number. It doesn't have a nice simple form to it. So this one, because there's only a single x here on this side, it's easiest to solve it this way, where you take the natural log of both sides and then solve it that way. So I did not try to rewrite 10,273 as base E. I just solved for x. And this one here, the reason why I chose to do this 3 log base 3, you could do 7 log base 7 on this side, and you get the answer might be slightly different. I think it'll be, yeah, it'll definitely be different, but you should get the exact same number here, 0.09. It's just going to look different with the log base 7 rather than log base 3. But I chose this strategy here because both 7 and 3 are prime numbers, and they cannot be written in the other form. Like 7 isn't 3 to some power. It's just 7. So that's the reason why I chose kind of this strategy. Now this strategy is the exact same thing as just saying, let's take log base 3. Let's take log base 3 of both sides, and that log base 3 cancels with this x plus 2. It's the same idea. It gives you the exact same work. But that's the reason why you'd use this strategy when there's powers, there's x in both exponents, like there is in the 2x plus 1 and x plus 2. If there's x's in both powers, then this strategy works out nicely. And it's probably going to be the easiest thing to do than following any other strategy that I showed you. For logarithmic equations, if we can get only one logarithm by condensing, then the equation tends to be a bit clearer on how to solve it. In this case, we only have one logarithm. So to solve it, we're going to take the power, or put both sides into the power of 5. And the reason why is because 5 cancels with the log base 5. So those cancel, leaving us with just the argument of the logarithm. So we have 5 squared on the other side, and 5 squared is 25. And then all we have to do is add 7. So we get x equal to 32. And you can check your work real quick. If you plug 32 into here, 32 minus 7 is 25, and log base 5 of 25 is 2, because 5 squared is 25. All right. For this one, we need to condense the two logarithms together. They are subtracting here, so we're going to use the property of logarithms that says if they're subtracting, it goes to division. So we have log base 4 of the first divided by the second equals 1. And now to get the logarithm away from, or to get rid of the logarithm, we do the inverse operation, which is exponentiation. So we need to put 4, put both sides in the power of 4. That way this cancels, and 4 to the power of 1 is 4. So that gives us x plus 2 over x minus 1 equals 4 to the power of 1, which is just 4. Now I need to solve for x. And the first thing I note, well, I should have actually started with the first thing, with the previous problem too, is that here x cannot be, it must be greater than 7. Because if it equals 7, 7 minus 7 is 0, and logarithms cannot have 0 on the inside. And if it's less than 7, then something smaller than 7 minus 7 is negative, which you cannot have a negative in there. Of course, our answer here is greater than 7, so there's no issue with that. Down here, x must be greater than negative 2. Anything less than or equal to negative 2 gives us 0 or a negative. And for this one, x must be greater than 1. And so because x must be greater than equal to negative 2 and x must be greater than negative 1, that's the same thing as just saying x being greater than negative 1, because this, x being greater than negative 2 is always true if x must be greater than 1, because negative 2 is less than 1. So that's our first kind of stipulation there. Now, at this point, we have x cannot equal 1, because if it did, we would have a 0 in the denominator. Of course, this is still contained within. So both x minus 2 and x greater than negative 2 and x not equal to negative 1, sorry, x not equal to 1, they're both contained within the statement of x greater than 1. Okay, with that talk aside, we can continue to solve this problem. I'm going to multiply both sides by x minus 1. That gives us x plus 2 equals 4 times x minus 1. Distribute the 4. And then get the x's by themselves. So I'm going to subtract x and then add 4 to the other side, giving me 6 equals 3x. Divide by 3, and I get x equal to 2. X equals 2, it satisfies every single one of these conditions. So x equal 2 is our answer. All right, for this problem, we need to condense both sides. These are both, all of these logarithms are base 10 because nothing's written there, so it's assumed to be base 10. Okay, on this side, I have an addition of logarithms. That means it goes to multiplication. The first times the second. And we have both base 10, so I can get rid of the logarithms by just doing base 10. You can also say the question that, well, if log base 10 equals log base 10, the only way that's true is if the arguments are the same. Either way, it's the same. You'll get the same result by giving us, that gives us 2x minus 1 equals x plus 3. I'm just going to move this 3 into the front, so it's 3x plus 3. Now I should note, however, some of the stipulations that x can equal. So for this first logarithm here, when does 2x minus 1 give you 0 or a negative? That's when x equals 1/2. It gives you 0. 2 times 1/2 is 1. 1 minus 1 is 0. So x must be greater than 1/2, I think. If it were 0, we would have negative 1, yeah, which is a negative number. X must be greater than 1/2 for this first logarithm. For the next logarithm, x must be greater than negative 3. Because if it was negative 3, we have negative 3 plus 3 is 0, and 0 is not allowed. And anything less than negative 3, like negative 4, for instance, negative 4 plus 3 is negative 1. Negatives are not allowed. Of course, once again, x greater than 1/2, that satisfies x greater than negative 3, because x is already greater than negative 3. What if it's greater than negative 1/2? Then just 1/2. I hope that makes sense. It's the idea that this is 1/2. If x has to be here, then x by default has to be in this set. Like if this is what we're saying is true, then this is already true. That's just what I'm saying there. Of course, log 3, the last one here, that's just a number, and 3 is a positive number, so that's fine. There's no errors with that. Okay, with that out of the way, we can continue solving the problem. To do this, we're going to distribute to 3, giving me 3x plus 9 I'm going to subtract the 2x to this side and then subtract the 9 to the other side. Give me negative 10 equals 3 minus 2x is x. So we get x equal to negative 10. But this does not satisfy that. Therefore, that's not a solution. And we got no other solution with this, so our answer is no solution. I'll just write solution. That's why it's important for you to check your conditions. What can x equal and what can x not equal, because this will arise when you're doing the work with the logarithms. All right, we have a single application problem here. We have money that's being invested, and we're asking with $5,000 invested at 14.7 interest that's compounded daily, how many years will it take to get $9,000? The formula for this is A equals P times 1 plus R over N to the NT. This is just the compounding interest formula. Since we're investing $5,000, we know P equals 5,000. The interest rate is a whopping 14.7%. That's a huge interest rate. If it's compounded daily, that means N equals 365. And we also know how many years, so we're trying to figure out what T is, to get A equal to $9,000. Plugging this all in, we get 1 plus 0.147 over 365 T. Now to solve this, we're going to use a little trick that's quite handy, and it uses once again that property of logarithm. First thing I'm going to do is I'm going to divide the 5,000 to the other side, and you'll see it's just the 9/5. I'm also going to simplify the inside into, hopefully it's a nice number. It is not. Okay, so I'll leave it. 1 plus 0.147 over 365. Okay, the trick is this. When you have some base, like on this side we have a base that's really weird, and we don't have any other logarithms or anything like that. The trick is that you can take the natural log or log base 10, or really any logarithm, but ln is the shortest thing to write, so that tends to be what we use. It's also the nicest function to use. You take the natural log of both sides, and what that does is it allows you to take the power here and move it out in front due to the property of logarithms. So now we have ln 9/5 equals 365t times ln 1 plus 0.147 over 365. And this is really just a division problem to get rid of the numbers around t. 365 times ln 1 plus 0.147 over 365. The same thing on this side. And that gives us, those cancel, just t on the one side. It was actually quite a simple problem to solve as long as you knew that trick. If you didn't know that trick, you'd have to do a change of base formula, which can take a little bit longer, and yeah, it would be a lot more annoying to solve. But now you do need to plug this into a calculator, and that'll give us an approximate year amount. So after I plugged it in, I got, you can round to, I guess, 4 decimal places. That'd be 9993. I mean, it's pretty much just 4 years, because our original problem said, how many years will it take? So it's approximately 4 years when you plug that all in.